This problem, z is square root of x squared plus y squared. So in the context of this is a complex random variable, but real part and imaginary part. So if you write it as magnitude and phase, magnitude is this is the phase. The question is, what is the density function of these, given the joint density function of x and y. So we'll consider this problem. So I'll consider this couple of different cases. I'm going to do, let me see how much we'll do x, y, zero mean, same variance, and the fifth parameter 0, rho equal to 0. And you may want to go home and try some different means. So you have non-zero mean, but still the means, and then zero mean, but variances are different. And the last case is when rho is also not zero. I'm not going to do all cases, but all cases are already done, but we'll go through some of them. And once you see how some of them are done, you should do. So remember when we say two random variables are jointly Gaussian, you have fxy, x comma y, some constant e to the power minus 3 terms here, right? So c e raised to minus 1 over 2, 1 minus rho squared. Then you have 3 terms. So x minus mu x the whole squared over sigma x squared minus 2 rho x minus mu x y minus mu y sigma x sigma y plus y minus mu y. So first I'm going to do the simplest case. The mean is 0, the variances are equal, and this term is not there. So x and y are independent. But you can go home and do all these different cases, and the results are more and more complicated. But the neatest result is what I'm going to do now. So in our electrical engineering parlor, this is the envelope of the signal, right? So a Gaussian, you can say complex Gaussian, maybe noise or whatever, or a signal. This is the envelope, this is the phase. Because if you write it like this is the envelope, right? The magnitude. So we want to find the distributions of that. Assuming these two are, what I'm going to develop, the theory is first good for any density function. But then we will specialize this. And it gets to be a little complicated, but you just have to have the patience and muscle it through, right? So we'll do so let's start with the distribution function. So by definition, by now you know how this is going to go. So z less than or equal to z. But z is given to be square root of x squared plus y squared less than or equal to z. So where is this region? Anybody? What? Yeah, right. So this is the equation of a circle with radius what? Huh? Radius is z? Absolutely. Right. So radius is z, you're right. Yeah. Right? All right, so where are we integrating in this figure? Anyone? Where? Inside the circle. So so I can integrate, you want to integrate nicely, so we'll integrate here. Then you push in the y-axis here. This is x, this is y. So tell me the limits. The joint density function should be, let's say integrate on x first, then y. So x goes from where to where? So this is a particular value of y. So what is this value of x? What is this value of x? Anyone? And the top limit? Huh? Okay, now how about y? Goes from where to where? See, you're beginning to understand, right? You want to integrate over here, so minus z to c. So that's good. So what's the problem now? Problem is to take the derivative of this, so I'll do it here. So look here, z is all over, so we have to do step by step. So derivative of remember the derivative is with respect to, remember too many variables, x, y, z, but derivative is with respect to z. Z is what we are talking about. So let's take the derivative of here with respect to z. So this integral is with respect to y, inner integral is with respect to x. So the derivative of the upper limit, which is 1, that's easy. This integral is with respect to y. So wherever you see y, you put the limits. What do you get? It will go 0 to 0 because you are putting y equal to z. So 1 multiplied by 0 to 0. There's nothing to integrate. Okay. Minus the derivative of this, minus 1. Substitute this again. 0, right? So the first, it doesn't contribute anything. The third step is the limits stay as it is. Derivative of the inside quantity with respect to this. What is the, here the limits is, this integral is with respect to x. Now we are here. We have already taken care of this. So let's do this. Derivative of this quantity with respect to c. What do you get? The derivative of this with respect to c. So derivative of square root of something is 1 over 2 square root of something multiplied by the chain rule, right? The derivative of the inside quantity with respect to c, that's 2z. 2 cancels. C over. So none of this is, you can guess it. You have to solve the problem in front of you. And then what? Multiply by? Wherever x is there, you substitute the limit. So square root of z squared minus y squared comma y. Then what? Minus, look at here, minus derivative of the bottom limit. What do you get? So there is a minus here, minus plus, otherwise everything is the same, right? I hope you see it. fxy, what do you substitute here? Huh? And the third limit is derivative of the inside quantity with respect to c, but there is nothing inside, right? 0, right? So this is the answer. So let me simplify this a little more and then I'll solve for this Gaussian problem. So let's do it here. So here we get, I'm just copying the last line. Minus z to z, z over square root of z squared minus y squared. But then you have two terms, right? Because this comes out together. So this is fxy square root of z squared minus y squared y plus fxy minus square root of z squared minus y squared comma y. So let me erase all this stuff. So now you need to you do, this is the formula you will be substituting, but now each of this case you do, I'm going to do one or two cases here, the rest you do it at home. So let me do the simple case here. So look here, rho is 0, so I'll write it here, right? Rho is 0, 0 mean and same variance. So I'm going to come back here, I'm going to, so our density function, I'll write it here. xy, if it is 0, comma 0, sigma squared, 2 are equal, and rho is 0. If rho is 0, middle term is gone. So the joint density function now reads, the constant is, I think we did this earlier, right? E raised to minus x squared plus y squared over 2 sigma squared. So this is what I'm going to substitute there. So this is minus z to z, z over square root of z squared minus y squared, 1 over 2 pi sigma squared. Then I have this term twice, right? Look at here. Instead of x, I'm going to substitute this, square it, and add to y squared. So what do you get? Anybody? I hope you see this, because c squared minus y squared plus y squared divided by 2 sigma squared. Exactly the same thing here. So I can multiply this by 2, yes? Integration is with respect to? dy, right? So look here, y goes out, so I'm going to pull this outside. 2 cancels. So you have e raised to minus z squared by 2 sigma squared outside with a pi sigma squared outside. Then what remains is minus z to z. And I can also pull out a z here outside, right? Z is a constant. So I just need to integrate this. Yes? So how do you integrate this? Anyone? What is an obvious substitution? The first thing is, before you substitute, again, this is an even function. So this can be written as 2 times, right? 0 to c. So that much is right. Now how will you simplify it? What do you substitute? Z equal to? I want to get rid of the square root and so on. So what's the, not z, y equal to. So dy is, remember what is the variable? Y and theta, not z. Z is fixed there. So this is cos theta d theta. So let's see this integral. So when y is 0, what is the limit value on theta? When y is 0, theta is? When y is 0, theta is? When y is z, theta is? When y is z, z cancels, sin theta is 1. So this integral is 0 to pi by 2, 1 over y squared, z squared minus y squared is how much? Anybody? So this is z squared minus 1 minus cos squared. 1 minus sin squared, so z cos theta, right? That's in the denominator. Z cos. How about the numerator? dy is z cos theta, d theta. So this cancels. So what's the answer? This can't be that hard. Integrating d theta. Pi over 2. So that's the answer. So that I plug it in there. So 2 cancels. Pi cancels. So you get 0. Two and pi cancels, the rest will remain. So z positive. So this is Rayleigh. This is not gamma, Rayleigh. Because of the c squared here. For gamma, this will be c and z here. So you have a theorem here. If x and y are, look at here, this special case, if x and y are 0 mean equal variance, and the fifth parameter is 0, we'll see that that's related to independence. Then that, of course, you can see here. If rho is 0, you clearly see x and y are independent because this term goes away, it becomes the product. So I'll come to that, but you can clearly see rho represents its independence, right? Dependence or independence, because rho equal to 0, this becomes fxx multiplied by fyy, right? So rho equal to 0 dictates the independence, right? So when two Gaussian random variables are 0 mean independent and equal variance, then their amplitude is Rayleigh. If you can ask the same question: what happens if they have a non-zero mean? So you just use the density function and do. Let me do this case and see how complicated it comes. Just to show you one case, it's exactly the same formula. So this result, let me write it down here, so that you understand. So what we just proved is if x and y are 0 mean independent, because rho equal to 0, you get that formula. A Gaussian random variables with equal variance. So look at the conditions. You need 0 mean, you need independence, you need equal variance, you need them to be Gaussian. Then amplitude, which is square root of x squared plus y squared, is Rayleigh. That's the theorem. So you can pretty much be sure that if any of these conditions are violated, this result is not true. So you need all these conditions under which we showed. So let's just see how far we can go if they have not equal variance. And then this case is solved in the book. This will come out to be a Rayleigh density function. Yeah. For what? I mean, that is polar coordinate, right? That the A is R, your radius. Whatever. I mean, I just wanted to give you also a physical feeling. That's polar representation, if that's what you're asking. So in polar representation, this is Rayleigh, and we can actually do this also. So let me finish this, then I'll go into a independent case. So remember, y over x is, we already found this out. What's the density function of y over x? The ratio of two Gaussian. What is it? We just did it 5 minutes, half an hour back. What? Cauchy, right? And I don't know whether you remember, we also have studied that function. So let me just finish that case and see. So y over x is Cauchy, right? So let me call this to be phi. So phi is not phi. Y over x, let me call to be, let's say w. And this is Cauchy, right? This is what we studied, we did a little earlier, right? So now I want phi equal to tan inverse w. That's what we are asking therefore. So you know this, so w is tan phi, you have w equal to tan phi. So dw by d phi is sec squared phi. So f phi is what? So this is your y, 1 over dy by dx or dx by dy. Dx by dy is this, right? So that's dw by d phi, absolute value. There is only one dw, and w is known. Solve in terms of phi. So this is sec squared phi multiplied by 1 over pi. This density function is here. W is tan phi. So that's 1 plus tan squared phi. Tan squared, 1 plus tan squared is sec squared. So what is this density function? Anybody? All right, so you have another result. So the principal value of tan inverse W is minus pi by 2 to pi by 2. So the phase is uniform. So let me complete this here. The magnitude is Rayleigh, and then the amplitude is Rayleigh, and the phase, this one, phase is uniform. At least the principal value is from minus pi to, so if you go from pi to minus pi, it's going to be uniform in that region. Little later, maybe next class, actually we will show that these two random variables are in fact independent. It doesn't make any sense, but they are. All right, so before I finish, let me at least quickly do, so this case you look at in the notes, it's done in detail. I mean this, so let's know this. Remember, it's a question of just finishing it up. So this is minus c to z, z over square root of z squared minus y squared. Now, this is the case I'm going to consider. So the joint density function is sigma x, sigma y, e to the power minus x squared over 2 sigma x squared plus y squared over 2 sigma y squared. That's the only difference. Rho is 0 still. But sigmas are not equal. So instead of x, look at here. Instead of x, I should substitute this one. And this comes twice. So let me do term by term. So instead of this, I am going to substitute c squared minus y squared. And the other case is with the minus. But when you square it, it's the same. So I hope you see that I can multiply this with 2, right? And this is where the difficulty starts. This y squared doesn't go away, you see? All right, so you'll come up with this messy integral, how to solve it. So all right, so look through my videos. It's already there. I've gone through this. So remember, the c squared term goes outside. So you see e raised to minus z squared over 2 sigma x squared goes outside, right? And then you get integral minus z to z. Z we took care of it, 1 over z squared minus y squared, e raised to minus y squared. And again, since y is symmetry, I mean, it's an even function, you can write this from 0 to 2 times this one. So question is, how do you simplify this? Actually, so one way is you can, I don't remember exactly how this is, but you will get into a neat result, how you can expand either this because you can expand this as a binomial and then bring in gamma functions, etc. But you can see nothing is pretty from here on. This is not going to simplify to Rayleigh or anything. So that's a very everybody quotes this, but that's a very special result. On the other hand, if you do this, so what will happen here? Here, if you do that case, otherwise, so let's do the other one, see whether that's any easier. So if you do this case, integral minus z to c, although this is already here, then just this one. So this is 1 over 2 pi, the variances are equal, but you have e raised to minus x minus mu squared plus y minus mu the whole squared over 2 sigma squared dy. Again, you can see the problem. X is going to be replaced by this. So this will now read, instead of x, you have, what was it? X minus mu the whole squared plus y minus. So x, you have to substitute this in one case, and in another case you have to substitute this. Because of this minus, again, it's not going to cancel and so on. Again, this has been simplified to an extent. This is when you open this up, it comes in terms of a Bessel integral or something, and the whatever is that messy form you get is known as the Rayleigh density function, Rayleigh. Oh, so maybe if next week, if you have time, I'll look this up and come over. Especially this case, I believe you can simplify this to an extent. But these are all the cases you sort of, if you have time and energy, you can go through and see how the Rayleigh degrades. So the Rayleigh is a special case. When the two random variables are independent, zero mean, equal variance, the amplitude is Rayleigh. Every other case, it's messier.